All right, thanks for your patience in my lateness. So we're done with the first two modules that focused on conjugation and aromaticity. So those were related to basically alkenes. And now we're going to get into climbing the oxidation state ladder. So this module will be oxidation state 1. We'll look at alcohols, ethers, the sulfur variants of those called thiols and sulfides, and then amines. The next module, we're going to go up to aldehydes and ketones. Then we'll look at carboxylic acid derivatives. Then we have a separate module on carbon-carbon bond formation, and then we wrap the semester up with biomolecules, so carbohydrates, peptides, proteins, amino acids. So this is really all a build-up of that. And now is when we're going to start learning a lot of functional group transformations. And so the oxidation state is really going to help us kind of minimize the mental burden we need to put into doing this, since there's a lot of reactions. We look at the starting material, we look at the product, and then understand how the oxidation state is changing. And as we do that, we'll review mass spec, IR, and NMR so that we know that those functional groups are present. So we'll start off with alcohols. So the general abbreviation for an alcohol is ROH. So R is just a placeholder for the rest of the molecule. And as we'll see on this slide, there are different classes of alcohols, primary, secondary, and tertiary, based on the carbon that the OH group is attached to. So the way that these are named is you take the longest carbon chain, the alkane name, drop the E and add OL. So within the parent name, it's telling you that an alcohol is present. And then once you get beyond 2 carbons, then you have to specify where that OH is. So as we see in the first column of the chain length, that's the number of carbons. Then the second column is the class, like what type of class, specifically the carbon bearing the OH group. So methane becomes methanol, and that's CH3OH. So we've substituted an H for OH. And then we have the molecular weights, the melting and boiling points. So the OH group, as we'll see, because it can be a hydrogen bond donor acceptor, it impacts the physical properties quite a bit. And the two main ones for us are melting and boiling points. But if you go on to take more chemistry courses, or if you're polymer science, having these functional groups in a molecule affects the properties that you might be interested in altering. So ethanol, CH3, CH2OH. Ethanol is the alcohol you can drink. It's the alcohol that's in beer, wine, vodka. That's the common alcohol. And you know, when like beer is brewed or wine is fermented, that is a byproduct of those processes. So that you can drink and feel good. Methanol you cannot drink because that does something very specific in the body that leads to some harmful consequences. And that is the reason that happens is due to the oxidation state. So when we get up to 3 carbons, now you see that we have 2 different classes, primary and secondary. And that's just where we're placing the OH group on the chain. So this is the carbon that you're classifying that's bearing the OH group. That carbon is bonded to one other carbon, so it's primary. For 2-propanol, that carbon is bonded to 2 other carbons, so it's secondary. For the 4-carbon chain, now you'll note we have all 3 possibilities. And if you look at the names, we can have a primary, a secondary. The tertiary one results because now the chain is branched. So this is not a butanol derivative, it's a propanol derivative. So that's 2-methyl 2-propanol. The OH group, regardless of the class 1, 2, or 3, the signature in the IR looks the same as we'll see. It has that broad signal about 35 to 3,000 wave numbers in the IR. So you can't really tell what class it is. But one thing I do want to point out, primary, secondary, tertiary. The carbon bearing the OH group, when I say oxidation state, all we're doing is counting the number of bonds from the carbon to the heteroatom. So C to O, that's 1 bond. We call that an oxidation state of 1. Of the 3 classes, primary and secondary, that carbon has at least 1 hydrogen attached to it. A tertiary alcohol does not have any hydrogens. And that's important when we start talking about the reactions of alcohols. So if you think about, if I want to take that carbon and oxidize it, or increase the oxidation state from 1 to 2, it's making a new functional group. And to do that, you have to have at least 1 hydrogen. So tertiary alcohols are a special case in that they don't undergo some of the reactions that we'll see. So we have a question about naming, because you'll get a couple of those on the module exam. You'll see 1 or 2 on the final. And now that we're studying oxidation state formally, the IUPAC rules state that the parent functional group is related to the highest oxidized carbon of the chain. So when we look at all the carbons here, that carbon is bearing an OH group. It's the highest oxidation. The functional group is an alcohol, so it has to be named as an alcohol. When we find the longest chain, so I would say it's probably that's the longest chain, that gives us the parent alkane name. And then we need to specify what carbon that OH group is bonded to. So as a review of nomenclature, let me just kind of snake around the longest chain. Then if we count the carbons, 1, 2, 3, 4, 5, 6. So it has to be a derivative of hexane. We have 2 things outside of that, snake that we circled there. So we have the alcohol group and then the methyl group. So that carbon is at oxidation state 1. So the hexane becomes hexanol. But now we have to specify the position. And so in green, I'm going to number the chain the correct way. We would say it's 3-hexanol. I think nowadays that number is actually shoved into, like historically it was this, or that number specified the OH, but now to make things a little clearer, the number is put before the actual functional group. And then we have to take care of that substituent methyl, that's at the 4 position. So we can just add all that together. And we would end up with A is the correct response for that. So the ambiguity, again, about numbering that chain is which end do you start on? So in blue, that's the wrong way to do it. So let's write the name that would result and then compare it to the other one. So that would be 3-methyl-hexane 4-all. The reason that path is incorrect, the parent functional group has to get the lowest number possible. That's the way the rules are written. So if you take 4 plus 3, and then 3 plus 4, they both equal 7 in terms of the total. This one, again, is not correct because you're giving a higher number to the parent. The parent always has to get the lowest. So of those rules, the highest oxidation state becomes the parent. Then on the chain, it has to get the lowest number. These other ones, so that choice B would be that blue answer. These other ones are incorrect because they have not identified the longest carbon chain. So, doing nomenclature problems is like, I don't know. Once you do enough of it, you've done them and you don't want to do any more because you sort of see what the rules and trends are. But as we go through these oxidation state 1 functional groups, the names have their own little bit of flair. So ethers are named differently. Amines are named a little bit differently, but I think you'll see the overall trend. So here's a question about the effect of the OH group on the boiling point. And if you look at the progression of those alcohols, apologize, my screen versus what you see is kind of different due to some stuff. What can you conclude based on the structure of these relative to these boiling points? So if we add in the classification of the alcohols, the trend is primary alcohols will have, in general, higher boiling points than secondary or tertiary. And really that's sort of the availability of that OH group to hydrogen bond. Another way that I like to think about it in terms of like food, so here are two constitutional isomers of that C4. You have the primary and the tertiary. The primary boils at 116 and the tertiary 83. So they had the same molecular weight. So we can't attribute a change due to molecular weight. And if we think about what boiling is, you have these molecules, the hydrogen bonding is increasing the boiling point. But the difference between these two, the linear ones are like spaghetti, when you cook like angel hair pasta, which is my favorite, when you mix it up, they become entangled, right? So these linear ones become entangled with one another. That's another effect that the heat has to overcome. These tertiary ones look more like M&Ms. So M&Ms really can't entangle one another. They just have limited surface contact. So as you increase the chain length, primary has this entanglement along with the hydrogen bonding. So that adds a little bit more to the physical property. So this would be choice B is the correct answer. So when we're given some data, how do we know that an OH group is in there? And I have these tables for each functional group we'll study. The green highlight means that will increase your confidence quite a bit, that it's going to have an OH. Yellow is sort of in between, maybe, maybe not. Not sure if any of these tables have red in them, but in IR, you will definitely see that broad OH stretch. And again, the reason it's broad is because it's hydrogen bonding. And when you think about that, it's not just like one hydrogen bond. The molecules, there's a lot of them. There's a lot of that going on with any one OH group. Mass spec. We haven't talked too much about fragmentation, but if you have the parent mass, if you subtract 18 from that, which is the molecular weight of water, and you see a fragment signal, that's a mild indicator that there's an OH group in there. Proton NMR for the H, you may or may not see a signal. And what I mean by broad is so something that spans a large number of ppm, say half a ppm broad, because your normal proton signals are pretty sharp, right? They go up, then kind of down. If something's broad, again, that's due to hydrogen bonding. And the reason you may not see these is based on the acidity of the OH group that it can exchange, and so you don't have direct evidence of it. In the carbon NMR, The carbon bearing the OH group typically falls within the range of 30 to 60, and again, depending on whatever else is bonded to that carbon. That's kind of a unique range that's giving you the indicator that C is bonded to O. Because we are in oxidation state 1, you would have to use the IR to determine, is that carbon belonging to an alcohol or is it belonging to an ether? And the OH group in the IR is what tells you the difference. So that region 1 there is your IR stretch. So what I mean by broad is if we draw like a line here where it starts and then there where it's kind of ending, you see how it's spanning a large distance of wave numbers on the x-axis. And really the way that I learned this, 42,000 years ago, was just looking at the shape. It's like alcohols are going to look like that. So we know this other functional group, the carboxylic acid, that also has OH, but it has this carbonyl. So when you see a spectrum, if you're trying to determine is it an alcohol or an acid, alcohols look like that, and then there's no carbonyl here as well. So then we know it's OH. When we get into the module with carboxylic acids, you'll see that OH, it does look different. It doesn't have this same, it's broad, but the shape doesn't look like that. And then it'll have that associated carbonyl. So to me, when I'm looking at the data, it's more of a visual thing than having to go to a table to say this region has this, so it has to be this functional group. And that's what helps me, sort of make these claims for different fragments. So that's the two atoms that define an alcohol. The oxygen, as we know, has 2 sigma bonds. One of them has to be to H. The other one has to be the carbon, represented by that squiggly line. The oxygen has 2 lone pairs. So we can say based on electronegativity, that's delta minus. The hydrogen's delta plus. So that OH has a permanent bond dipole. And with, this sort of subset collection of elements, OH is a hydrogen bond donor and acceptor. And I'll just represent that with water. So 2 water molecules on a flat white surface, not the best representation. So what you have to imagine is that each molecule is obviously 3D, but it is surrounded by a ton of other water molecules. So fortunately for life on Earth, water has these very unique properties, and with the Celsius scale, it's easy to get some milestones about melting and freezing at 0, boiling and condensing at 100. So why does the OH group affect that so much? So with a blue dotted line from one lone pair to an H. I'm going to call that the hydrogen bond. So the reason I drew the dash, and what's weird about calling it a bond, so this red line here, we interpret that as a polar covalent bond. So polar due to the difference in electronegativity, covalent because they're sharing, and that's our recognition of a normal bond. When we say hydrogen bond and use the dash line, there's not really a formal sharing between this oxygen and that hydrogen, so it's an attraction. And hydrogen bond falls under the general class called non-covalent. Interactions, so NCI. That's probably the one you're most familiar with. Non-covalent interactions is hydrogen bonding. I can tell you there's a lot of other ones that are very important, especially as we move towards Module 5 with biomolecules, and specifically like with DNA, the two independent strands are attracted to one another through hydrogen bonding, but they then organize themselves into this ladder type sequence due to another thing called pi stacking, where you have an aromatic ring, kind of looks like a sandwich, then one above it, another sandwich. They're attracted to one another through a non-covalent interaction. And I think life on Earth or Alpha Centauri or whatever other planets can arise from non-covalent interactions, not primarily, but it's very important. So not only the primary structure of how things bond, but once they are bonded, what do they go on to do? So because it's not a formal bond, it has a weaker energy. It tops off about 20 kilojoules per mole. But now if you imagine each water molecule has a ton of these other ones around it, the little bits do add up. So that is a little bit about the physical properties. Let's talk about the reactivity of the OH group. So I use this word here, ambiphilic, and that's basically saying that it has both basic and acidic properties. What dictates the outcome is the medium of the reaction. So the first one here, we're going to look at the alcohol acting as a base. So if the medium is acidic, so we have hydronium ion as our general acid, H3O+. We're in acidic medium. This has to be a base then. And then the action of a base is to supply electrons in a reaction. Oxygen has the lone pairs. It's going to abstract an acidic H to generate this other intermediate. So we would show the arrow pushing like this. So another cheap way of saying that is proton transfer. And that's important not only for mechanisms in this class, but if you do go on to biochem and you start learning about metabolism, your body is not using sulfuric acid as a proton source. So how do protons move under physiological conditions? It's through amino acids, which is in module 5, but conceptually, if you know how to push the arrows, you can shuffle those protons around. So hydronium is derived from water, and then oxonium is derived from alcohols. And then we get the conjugate base over their water. So that's a mechanism. A mechanism is showing how the electrons move. And one of the things I would strongly encourage you to put the time in this semester is conceptually understanding how to draw mechanisms, because you're going to learn so many reactions that it's going to be tough to memorize them. If you're good at memorizing them, then maybe you'll be able to manage things. But if you understand how the electrons move, what the reagent's doing, you don't have to stress yourself out about memorizing every single little detail. So since we're in acidic medium, the oxygen can only be neutral or positive. So notice in here we have not drawn O- anywhere. It's not allowed under an acidic medium. So the reason this is called an intermediate is because now we have this OC bond that wants to break or ionize. So if we take the electrons in that bond, we put them onto the oxygen, that produces water, which is a stable neutral molecule. And then notice what happens. That plus charge has to migrate from O to the carbon where it left from. And so that was the basis for the SN1 and E1 reactions we learned last semester. So that was the basicity. Now we're going to focus on the other kind of reactive motif of the OH group, which is acidity. So we have our same alcohol. It has its same lone pairs. I'm going to draw this out like that now to actually show the OH. But now we're under basic conditions. So the reaction medium is basic. We're going to use this reagent, sodium hydride. So Na plus H minus. This is a pretty strong base. The pKa value of this OH group is about 16 to 18. That base now is going to abstract that H. We then break the OH bond. And now the oxygen ends up negative because it has now 3 lone pairs. And notice the name changes. So it ends in IDE, and that typically means a negative reactive intermediate. On the prior slide, it was called oxonium, IUM, those are typically positive. So the other product from this is hydrogen gas. And I think that pK is about 38 to 40. And so if we recall from organic 1, we have a strong base, a weak acid. If we look at these pK values, the difference is greater than 5, so the equilibrium is going to lie to this side. It always favors the weaker acid-base pair. In terms of the mechanism, as opposite to the other conditions, the oxygen can be neutral or negative. So you notice you don't see any positively charged oxygens now. So as we start learning more and more reagents, you'll want to understand, is this generating an acidic medium, a basic medium? How do I need to account for electrons and formal charges? Any questions? So the pKa value is about 15 to 18, and that is so if these different alcohols, primary, secondary, tertiary, if they're all OH and the H is what's being deprotonated, why isn't it just like one value? Why is there a range? Well, whatever is bonded to that carbon can affect the acidity of the OH group, either through induction or resonance. So as we progress along here, we have to get the sweatpants on because we're going to the buffet and we're going to be eating a lot. You want to pull those concepts in, electronegativity, induction, resonance, as you try to explain these subtle differences. And what I would caution you against, don't try to convince yourself of something that isn't true or some new concept to explain things. Just go back to the fundamentals of what you know. So an example of that, we have these two molecules with 6 carbons each. Cyclohexanol has a pK of 16, and then this one, aromatic phenol, is 10. Now, what we need to explain is, if OH is OH, why are these numbers so different? And really what we have to do now is look at the product of each when it's deprotonated. So let's just say we treat this with sodium hydride. We do the deprotonation. Then we'll use the same base here, sodium hydride. We can still see that sodium is sodium, O minus is O minus. So how is the rest of this structure affecting that acidity? So phenol is much more acidic. So this product has to be more stable. And the reason it is because of resonance. The negative charge can be delocalized into the ring. So we can take a lone pair push it down to make an OC pi bond, and then that pi bond can push electrons out to that position to make a resonance form. So the charge went from oxygen to carbon, and then from this we can draw two more where that negative charge goes to the para position and back to the other ortho. So a reasonable explanation would be the negative charge is unhappy, and it's able to spread out the unhappiness over multiple people or places. And with the cyclohexanol, it's stuck there, so it's really angry. It can't do anything. So that's part of what I mean by when you're looking at, not only the specific zooming in on the functional groups, but overall, how does everything else explain these differences? So what are some best practices as we start learning the functional group transformations? So to be honest, those are probably the things you can memorize, like an alcohol being oxidized, what does it form? But the nature of the reagents and the mechanism, how you draw out the electrons being pushed, this is what you'll have to practice quite a bit more. And to help sort of put boundaries around that so we don't get too crazy in explaining things that are unreasonable. All reactions will have a nucleophile and an electrophile. A subset of that when you're dealing with protons is acid-base. So acid-base is only concerned with how protons move. Everything else, there's a nucleophile, there's an electrophile. The nucleophile is supplying the electrons, whether they come from a lone pair or a pi bond or wherever. The electrophile is accepting them. So that's the Lewis acid-base definition of things. Our curved arrow will always start from the nucleophile. Where are the electrons originating? The arrowhead has to point to the electrophile. Where are they ending up? And you can help yourself understand that, again, using electronegativity. That's going to help quite a bit. So where should the arrow point? When you look at a reaction, if you're given the starting material, I would say number the carbon skeleton in a meaningful way. It doesn't have to be the IUPAC nomenclature way, but number it so you keep track of the carbons, what are their oxidation states, so that you can see what's being broken, what's formed. That's usually helpful, as we'll see in a module too, when we start forming rings from things. You can take a long chain, cyclize it. How do you know what ring size it's going to form? Generally speaking, as a fallout from the Lewis dot rules, if you form a new bond, you have to break an existing bond. So we can't have something attack carbon and then carbon end up with 5 bonds, because we know that's not correct. Acidic media will only have neutral or positively charged intermediates. Basic media, neutral or negatively charged intermediate. And the biggest sort of advice I can give you, even though on the exams you don't have to draw mechanisms or stuff like that, is just to practice how electrons flow so that you develop the intuition of understanding how the different reagents act on different functional groups. So this is a review slide of some reactions we've seen already to access alcohols and ethers. So we're not going to spend too much time on these because this chapter is more concerned with sort of a couple other ways of generating alcohols. So as we left Organic 1, we were looking at alkene addition reactions. So one of those was hydration. So you can take an alkene, you can treat it with acid, and that's going to do a hydration. So I'll just draw this H in there so that you can see it's added OH across that pi bond. And so that makes a secondary alcohol. Does anyone know the name of this reaction? What streaming platform is Game of Thrones shown on? HBO. So yeah, so HBO is hydroboration oxidation. If you thought it stood for home box office, but so that, if you look, it's still adding water across the pi bond, but now you're ending up with a primary alcohol. So this is, one of those sets of conditions where overall you're still making an alcohol, but the nature of the conditions is going to favor one class over the other. The next one was called dihydroxylation. So maybe you don't want primary or secondary, you like both, so you end up with primary and secondary. Each carbon of the alkene is getting an OH group. And sort of some of what we saw with the strategy of synthesis, if this is what you wanted to end up with, that's fine. But if you had to take this on further, you now have this conundrum where you have a primary and a secondary alcohol. But say you wanted to do something at the secondary alcohol but not the primary, how do you get around that issue? Or you want to do the primary and not the secondary? Another way to make alcohols was halohydrin formation. So notice, just like with the hydration conditions, this is also producing the more substituted alcohol that you can get. You can actually take that alcohol and convert it into an ether. So if we treated that with, say, sodium hydride and THF as the solvent, we know the sodium hydride would do an acid-base reaction. So now we have something that's a nucleophile, a carbon that's an electrophile with a good leaving group. So that will close down to cyclize to this ether. we can take the alkene directly to an ether with a reagent. Called MCPBA. Notice this is not your typical benzoic acid because it has this second oxygen. It's a peroxy acid. So one of those oxygens gets plunked down on the alkene, that generates an epoxide. So I know I had to start late. I don't want to end too much early, but let me just introduce this before we get too much further in. Where we're going with this, we're going to look at these different functional groups, the nature of the carbon hybridization, review the oxidation state, and then from that, we're going to move back and forth. 1 to 2, 1 to 3. So when the number increases, that's called an oxidation. When it decreases, that's a reduction. So within those two general things, we're just going to learn the reagents that do it. So as long as you can track the oxidation state and then classify oxidation or reduction, you'll have an idea of what is happening. So hopefully through that classification, it's not too much memorization of stuff, but that's what we're going to do is how do we make alcohols, ethers through oxidations and reductions. So we'll pick up with that on Monday.